take up that symmetrical frame analysis, symmetrical frames. This is another special type of problem which I wanted to take up, analysis of symmetrical frames. So one general rule is always whenever the frames are perfectly symmetrical, they are not undergoing any sway. That's the greatest advantage. They are pure non-sway type of frames. All symmetrical frames, they are non-sway just like beams. So symmetrical frames also non-sway type of frames. Example of those symmetrical frames are like this. See this particular frame, 2EI, EI, and this may be H, H, L, this is W per unit length. So this is one type of example of perfectly symmetrical frame. Perfectly symmetrical means you have to examine with respect to geometry, that is the length, height, everything, as well as EI value, that also you have to examine. Suppose if I give here 2EI, then it is not symmetric. You have to check in the frame the geometry, the height, length, everything, that should be symmetric about a line. So geometry wise, moment of inertia wise, as well as load wise, everything. Here only this one more concentrated load, if it is given, then it is not a symmetric frame. Symmetry means it is with respect to load, geometry, as well as moment of inertia. That you have to make sure first see everything with reference to these three aspects, judge whether it is perfectly symmetric. So this is called single bay, single story type of frame, symmetrical frame, or you can have this type of frames, H1, H, L, L. Load may be like this. Here, central concentrated load, EI equals constant. This is also perfectly symmetric because EI value is constant, perfectly symmetric with respect to I. Geometry wise also it is perfectly symmetric, load also perfectly symmetric. So this is called single bay, two-story type of frame, or you can have this type of frame. This is also, this you can have varied length, then also it is perfectly symmetric. So these two same length and same height. This is L, L, this H2, H1, H1, this is H. And loading may be symmetric. So here this may be 2EI, 2EI, this EI, 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 EI. See, this is also perfectly symmetric about this central line, about this particular line. Symmetry you have to check geometry wise, as well as moment of inertia wise, as well as load wise. It is perfectly symmetric. This is called two-bay, two-story frame. All these type of frames we call it as symmetrical frames. And one advantage already I told, they are all only non-sway type of frames. They will not undergo any sway. And whatever happens on left side of symmetrical line, equal and opposite will have on the right hand side. So suppose if you call this as AB, this as CD, moment MAB is equal to minus MCD. Here, suppose M is the moment, MAB, here it is minus M. That's all. That you have to check. And analysis also can be done only by considering one half of the frame. Instead of the entire frame, you can just consider one half of the frame, that is one half about that symmetrical line, and do the analysis. Suppose if you take this frame, you can do analysis only for this half. If you call this as A, B, C, D, you can do analysis only for this half. This is a dummy point which lies on that particular line. This line cuts the member of the given frame, and that cut member, whatever that point which is there that you call as C1, you can do the analysis only for joint AB, and joint C1 you need not consider whenever this line cuts that particular member and finish off the analysis. Whenever this line cuts the member, the stiffness of that cut member, you have to take it half the stiffness of the original member. That's all the change. And here also this is cutting, and you can just take only one half of the member by taking member like this, taking only one portion towards left half of the symmetric line, and you can do the analysis only for this particular frame. That's non-sway analysis only. Here of course the symmetric line passes through this center column, right? Whenever it passes through the central column, this central column is not subjected to any movement. If the symmetric line passes through the axis of the member, you can take that the member moment, end moments as 0, because you are taking half the frame only for the analysis like this, perfectly half the frame, and this is the symmetrical line, and this member is not at all coming to the picture, and that you can take it as 0 only. You can finish off that particular analysis only for this frame. That is this joint, and this joint only you have to carry out the moment distribution. Actually the work involved will be almost half when compared to the total problem. Now we will take up an example and see how you can work such problems. So we will just take up a problem, symmetrical frame. Of course, symmetry with a symmetrical line cutting the member I will take, because whenever that symmetrical line cuts the member, you have to take that stiffness as half that particular value. So that's why I will take that particular example, cutting that member. So we will take up this example. So I will take up an example. Like this. A single bay, 2-story frames. So this is 3 meters, 4 meters high, and span 6 meters, and EI value, this is EI, and this is 2EI, and loading I will take so 50 kilonewton per meter, 100 kilonewton per meter. Any loading you can take, it doesn't matter, because since I have solution, straight away ready-made solution, I will just take up this particular example and I will explain the procedure involved. So first step, of course, that you need not repeat the member end forces, only the end members you have to take, because all the members we are not taking, only half of the frame we are taking. So that particular step you can skip straight away. You can go for, you just indicate it, only this. Since the frame is a symmetric frame, is symmetrical, only one half of the frame shown in figure can be analyzed. Shown in figure can be analyzed and only non-sway analysis to be carried out. Analysis to be carried out. These are the two important things which you are noting here. That is, it has to be a non-sway frame whenever it is perfectly symmetric in all respects. It is a non-sway frame only, it is not sway frame. And in that particular type of non-sway symmetrical frames, only one half of the frame we can do for the analysis purpose. So here the symmetrical line is like this. This is line of symmetry, and the line of symmetry cuts the members A, B, C, D, E, F. So only one half of the frame about that symmetrical line, you can take it. And the point at which the symmetrical line cuts these members, you can take it as fixed always. That also you have to observe. And this is the dummy point. This is C, F1 I will call. This I will call it as E1. They are not the regular joints of the frame. It is only lying on the symmetric line that we need not consider in the analysis. Only this point A, point B, C you can consider for the analysis. And the stiffness, straight away and right, this K of this member, you can take it as half the stiffness of the regular member, KCF. That's what I told while explaining that. This is very important thing you have to remember. That is stiffness of that particular member which has been cut by the symmetrical line, you have to take half that the regular member. So this regular member stiffness, it is I by L because both ends are continuous. I by L means it is 2I by 6, it is I by 3. Half that particular value of I by 3 we have to take. That is half of I by 3, that is I by 6. So similarly, this member stiffness K, you can take half of K B value, that is half of KBE is again 2I by 6, it is 2I by 6, it is I by 6. And stiffness of this member, relative stiffness, K is equal to, it is I by 3, that is no change. I by 3 only I by L because both ends are continuous. Here also K you can take it as I by 3. I am writing the K values in the diagram itself, so straight away I can work out DF or by the calculation. So distribution factor, so at joint B, joint C, only at these two joints I have to find out the distribution factor, and members B at B you have 3 members, BA, BC and BE1. This I will say BE1, I will write it at the center because it is coming at the center, and this BC. Then here I have CB and CF1. So the stiffness, it is for BA, it is already written I by 3. I by 3. For BE1,
I by 6.
It is I by 6. This is I by
BC. I by 3.
It is I by 3. Oh, this is I by 4. Sorry. You can see BA. I by length, height I have taken 4.
Yes.
That also I have varied. Right? This
Yes,
BE1, it is already determined how that particular value of BE, that's I by 6. And BC, it is I by 3. CB, I by 3. And CF1, it is I by
6.
6. So you can find out the total stiffness, value I by 4 plus I by 6 plus I by 3. So 12 is the LCM. You will get here 3 plus 2, 5 plus 4, 9. 9 I by 12 you will get. Therefore, distribution factor will be I by 4 by 9 by 12. You will get 3 by 4. I have the value here, 4 by 3. Yeah?
Yes, sir. 1 by 4.
Yes, 1 by 3.
1 by
Yeah?
3.
Check, because this is 9 by 12. 9 by 12 means, is it 12?
Sir, 1 by 3.
Yes, 12 is the LCM. 3 plus 2 plus 4, that is 9 by 12. So I by 4 divided by 9 by 12, it is 3 by, correct, 3 by 9. 3 by 9 means it is 1 by 3.
1 by 3.
So the next one is here 2 by 9. Here I will get same as 1 by 4 by 9.
Yes, sir.
Because BC is I by 3,
0.444.
it is 4 by 9.
Yes, sir. 4 by
Then
9.
for CB, CF1, the total stiffness as it will be 6 CB LCM, it is 3I by 6, 2 plus 1, 3. Therefore, or this is I by 2. So, therefore, this I by 3 divided by I by 2, this will be 2 by 3, this is 1 by 3. So, you can sum up these distribution factors, it has to be 1. That's satisfying. Here also sum should be 1. Here it is 3 to 5, 4, 9, 9 by 9, it is checked. So, like this, you have to do the distribution factors by taking the stiffness of the cut member by that symmetrical line by equal to half. Then you can carry out the norm-scale analysis. Third step. First step, you have to write this clearly. Second step, this distribution factor. Third step, the norm-scale analysis. That is similar to what we have already done. For that, first, you have to find fixed end moments. So that straight away you can find out fixed end moments. You have to find out for joints C and D. That is M, C, F1. That is nothing but MCF itself. That's same. That CN, it is same for this as well as the regular frame. It is same end. That is nothing but minus 50 into 6 squared by 12, that is minus 150. And then MBE1 is equal to MBE, of course, bar I was writing, MBE1 equals MBE minus 100 into 6 squared by 12, that is minus
300.
300. Then you carry out non-sway moment distribution. Non-sway moment distribution. Right? You prepare the table. Right? Joint A, member AB, B, BA, then BE1,
BC.
then BC, then joint C,
CB.
CB,
CF1.
CF1. And that F1 and E1, I told you, we need not consider. So just add this, and distribution factor for AB it is 0 because it is fixed, and BA it is 1/3, 2 by 9, 4 by 9, and 2/3, here it is 1/3. And right fixed, then moment, that is 0 here, 0 here, and only in CF you are going to get, that is here, minus 150, then BE. B is here, it is
minus 300.
300. The rest are all 0. So you can do that and find the balance. Here no balance, here it is plus 300, that divided by 3, it is plus 100, 300 into 2 by 9,
66.
so that will get 66.6,
7.
then 133.4. You see this sum
Yes, sir.
is 300,
0.
it is minus 300, 0, then here it is minus 150 divided by plus 150 is the
Plus
balance
150.
moment, that into 1 by 3, it is 50,
100.
here it is
100.
100, that's all. Then do the carry over, here it is 50, half the value, here it goes to 0, and B1 to E1B, it goes because E1 I have not considered, you need not transfer, don't bother about that. Then BC to CB, it is half this value, 66.7, from CB to BC, it is 50, here CF1 to F1C, it goes. Again, do one more balance. So here it is 0 and here
50.
it is minus 16.7. That's 50 into
Yes, sir.
1 by 3,
Minus 16.7.
16.7. Then this is minus 11.1,
Minus 11.1.
minus 9.1 and minus 22.2. Then here it is minus 44.5 and 22.2. So the minus.
Minus.
So this is also 0. Then do one more carry over balance. Like that, 2 carry over and balance you have to do. I'll write the final moment after doing that, because here also you have to stop your watch whenever the balance moment becomes very, very small. 2 more cycles you can do, then you will get final
Moments.
non-sway moment, because the balance moment becomes very, very small. That you will get 45.3. Here you will get 89.5. Then minus 240.3. Then you will get 150.8. So this sum is minus 240.3, definitely 89.5 plus 158.8.
Plus 240.3 minus 2.
Automatically
0.
satisfied. Lastly, you get 120.2 here, and this minus 120.2. So these are your non-sway final moment distribution. So now from this you can write NAB, which is the moment here, which is 45.3. This is the last step. So this I told you, the moment, whatever happens on the left side, equal and opposite happens on the right side. So that will be exactly equal to and opposite to
Minus.
MDE. MDE is minus 45.3. Straight away you can take it, and MDA is equal to 89.5, that is equal to minus MED, and MBCD. This is either BE1 you can take it, or BE itself you can take, because same and B, whether for BE1 as well as BE, it is same and B only we are referring to. So you can take that BE1 as BE itself, so that is minus 240.3, that has to be equal and opposite to minus MEB. It will be equivalent opposite. So then MBC is equal to 150.8, that is equal to minus MEF. Then MCB is 120.2, that is equal to and opposite to minus MFE. And lastly this MCF. CF and CF1 are same, that is minus 120.2, that MCF is equal to MFC minus MFC. These are our final end moments. MAB, MBA, MBC, MCB, same equal and opposite will be here. So whatever happens here, equal and opposite, you will get moments at ends of each member. You can plot the bending moment diagram. That's about the analysis of the symmetrical sway frame. And of course, symmetrical sway frame, whenever the symmetry line passes through the member, this making stiffness half, you need not do in that case. It's a regular thing, and this F1, E1, whatever we are getting there, we are getting regular joint itself, F and C in that. Except that there is no change. You can try that particular example on your own and come out with the result. So same type of frame, I will take it 50, 100, then 6 meter, 6 meter, 6 meter, 6 meter, 3 meters, 4 meters. So this is 2 EI. Or I will take EI is equal to constant, and you can do the analysis. Here symmetrical line passes through this member, and these joints are regular joints, you can take it. This will not come into picture at all. There straight away the moment you can take it as 0, except that there is no change at all. And with this, the moment distribution, all type of problems, be non-sway frame, sway frame, and in that the pure sway frame and symmetrical frame. The last two are special type of thing. With this, we have touched upon almost all category of problems you will come across. So with this, all moment distribution type of problem over. In the next class, we will take up Connie's moment distribution. Thank you.